Okay, so here we are doing video lecture June 29th, AMT 162 aircraft rigging and assembly and rigging. I think I have my computer set up to be able to do this correctly on YouTube. So today, as you see, you have your lecture video, and we're going to be going over alignments and balancing. Most airplanes are fully cantilever or with a minimum of external bracing, so assembly is pretty straightforward. You must follow manufacturer's maintenance instructions. General assembly procedures go as follows. You want to level the fuselage. That means leveling it laterally and longitudinally. Ideally, it would be inside a hangar to minimize wind currents. If hangar is not an option, aircraft should point into the wind. Nose points into the wind. Make sure to use manufacturer's level points in plumb bob or spirit level. Here's a picture of your spirit level and screw locations as an example. Continuing on with general assembly procedures, install wings and torque wing bolts, install horizontal stab and vert stab, torque bolts, perform alignment check, install movable control surfaces, install and rig control systems, and then of course a test flight would be done to verify control responses and flight stability attitude. Our wings, alignment checks on wings. Most modern wings have very little adjustments available, usually only angle of incidence. Wing mounting bolts are on eccentric bushings or serrated bushings. You can rotate to change the angle. And here we have a picture of these eccentric bushings. It's pointing to right here. You may need to use special incidence boards or just universal prop protractors for initial settings. This is still talking about wings. Either of these tools must be installed at manufacturer specified locations. So if your aircraft requires special tools, the manufacturer will say that, and you need to know to use these tools at certain locations that the manufacturer has set for them. This is a diagram of a typical incidence board that might be used, and shows you here the chord line of your wing, how you set your incidence board up here. You have a straight edge and an adjustable level, and here it would be your bubble level. Alignment checks for wings with V struts. A couple examples are the Piper Tripacer and the Piper Cub. These can usually adjust dihedral and angle of incidence. Procedure for alignment checks of wings with V struts. You want to level the fuselage laterally and longitudinally. Check and adjust dihedral. Use dihedral board. Position at manufacturer specified position. Adjust length of struts until bubble is centered. Here is a picture of that. You have your dihedral board up here and where you place your level. Next, you'd want to check and adjust the dihedral. Some aircraft use strings stretched between the wingtips at specified chord locations. You'll adjust the struts to get specified dimensions between string and wing root. Then you would want to check and adjust angle of incidence. Use incidence board or just measure angle with prop protractor or a protractor head of a combination square. Adjust rear strut to get proper angle. And talking about alignment of engines, you always want to use manufacturer's specifications. The engine is usually parallel to the longitudinal axis. Mounts usually just bolt on with no adjustment provisions. Be sure to use proper shimming or washers, bolts, torques, etc. as specified. So engine alignment checks as far as engines is pretty simple. It's usually bolt on, bolt off. There's not really any necessary alignment checks as far as the engine goes. It either fits or it doesn't. Alignment check on our empennage. Most are cantilever with fixed positions. Ensure that all bolts are correct part number and torqued in proper sequences so as not to cock the empennage when assembling. If you have a wire braced empennage, this uses streamlined wires to ensure they have proper tension using a datum board and is flat with airflow. This decreases the vibrations and drag. These must replace streamlined wires with streamlined wires only. So they have to be replaced with the same wires. Do not use round cable as replacement because of vibrations and different expansion rates. I don't know why that's in a different font. Whatever. You want to check the horizontal stab, dihedral, and angle of incidence. You do this basically the same as the wings. May or may not be adjustable. It depends on your aircraft. Check vertical stab, the fin. You want to check it vertically. Measure from like points on both horizontal stabs and should be equal measurement. The fin may be offset slightly to compensate for spiraling slipstream. So here is an example checking your fin vertically. String or tape measure the lateral datum. So you're checking this vertically on both sides. If suspicious, run string through control hinges. Should be able to be centered in all hinges. If not, then hinges are misaligned and will bind to control movement. Note applies to all control surface hinges, hinge lines, not just the empennage. We have our symmetry check, which some of you have completed in lab so far. To ensure the entire aircraft is aligned properly, meaning symmetrical. So this is our symmetry check. We want to measure between specified points on aircraft. Like measurements should be equal within manufacturer's tolerances. You may need to use a plumb bob from points and mark on the floor and then measure, especially on large aircraft, which most of you, as you've seen on the King Air 200, that's what you should be doing. This is a diagram of how you would do the symmetry check, where you're checking that symmetry. Rigging should be checked during all required inspections and anytime any control or major assembly, such as the wings, for example, is removed and reinstalled. Rigging means check systems and control surface travel and adjust as necessary. A test flight would be performed after reinstallation and adjust if need be. Control surface balancing. If you have a surface that is out of balance, It can cause flutter or buffeting of the surface. This can create control problems, uncomfortable ride, premature, and extreme wear. Needs to be checked after repairs or painting. This is a diagram for you to kind of compare some unbalanced conditions in flight controls. It's comparing it to a seesaw. So if your seesaw is not level, then it's going to be one side heavy. Here, up here we have our hinge center line or cord line, and you can see this has the tail end is heavy. And on this image below, they're showing you that there's been a balance weight placed in the front to bring this into balance. We want the moments fore and aft of the surface hinge line to be equal. The line at the CG generally adjusted by adding weight forward of the hinge line, as most repairs and paint are aft of the hinge line. Procedure for balancing control surfaces. Balance is checked and adjusted statically. Statically means the surface is not in motion. The surface is removed from the aircraft and installed on a balance fixture using the hinge bolts, usually a knife edge. Must be level and in draft-free environment. This is a couple of pictures giving you an example of us using some hinge fixtures. So we have a flight control here sitting on a fixture made for statically balancing. And this other diagram has a weight scale. We are not going to be using the weight scale method, but this is a good diagram to kind of point out some of the tools that you do need to use when balancing a flight control. You have your hinge center line here and your hinge fixture. Your bubble protractor, which you'll use to level the flight control. This says this is a rudder, so they're balancing a rudder. Rudder trim tab over here, and this is your weight scale. Another good picture just showing the cord line, bubble protractor, and this is just a diagram of a support stand is what it's pointing out here. This is kind of a similar image to what we'll be using for that project. Control surface balancing procedure. All trim tabs should be in a neutral position. The surface must be level. And we're going to measure whether the control surface is overbalanced or underbalanced, and if so, by how much. An overbalanced condition means that chord angles down at the leading edge, also known as nose heavy. An underbalanced condition, the chord angles down at the trailing edge, known as trailing edge heavy or nose light. This, so here you have an example of your overbalance here. So you have a nose heavy condition is overbalance. Tail down, underbalance here, your trailing edge is heavy. Manufacturer will give figures and formulas to determine the values that you need your control surfaces to be balanced at. If necessary to add weight, only do so at specified locations and check your balancing after you've added the weight. So this is an example of some measurements that you might see. Your surface, maybe your aileron, angle A should be 12.1 degrees plus or minus 5 degrees. Stabilator should be at 0 plus or minus, that might say 0.5. I think that's 0.5 degrees. So this is similar to what you'll see, some information you'll see in the maintenance manuals as far as wanting to balance your flight controls. This is an aileron showing you that it has some balance weights at certain locations. Here on our aileron we have this big weight that kind of allows it to be balanced or not. Same thing over here, mass balance weight. And you have a non-adjustable balance weight. Okay, so that's it. That's it for the lecture on alignment checks and control surface balancing. Don't forget to take the lecture quiz tonight by midnight. Well, 11:59 p.m.